on quantum computing, but now we are departing from tensor networks and we're going to do some actual quantum computing, all right? So last time what we did was quantum-inspired computing with tensor networks. We learned how to do differential equations solutions, partial differential equations, how to do machine learning with tensor network structures. Now we're going to concentrate on quantum computing and see how can we do Hamiltonian simulations with quantum computers, okay? So, as I told you about, we talked about the computational paradigms where we have quantum or classical data represented with a quantum or classical algorithms. So today, mainly, I'm going to focus on these two sections where we either have quantum data and we are computing it with classical algorithm, which is, for example, we are taking the gradient of a quantum circuit, which can be classified as a hybrid algorithm as well. Or we have quantum data and we are trying to do the algorithm, the entire thing as a quantum technique. So I'm going to show the differences. So first example, I'm going to constantly talk about different applications so that you can see, and I chose every single exercise from a research paper so that you can actually see what is cutting edge research, how it's done. There are different papers so that you have different flavors. So I'm going to first start with variational quantum eigensolver, which is quite similar actually to what you saw this morning, for example, in case of classification. And then we will talk about variational quantum thermalizer, and that is actually very similar to what you saw again this morning, generative modeling. We're going to basically we're going to learn a thermal state density matrix here. And then I will show you a quantum simulation, which means that basically, as I told you, quantum data with quantum simulation. So we're going to simulate a time evolution of a quantum state with a quantum computer. And then I'm going to show you a really neat example, which combines all these three things into one. And we will do some anomaly detection on data by using Hamiltonian learning, which is learned from a thermal state. Okay, so let's summarize a little bit the universal gates and what we are doing. So the thing is, quantum circuits are limited, okay? We have a limited set of operations that we can apply to a quantum circuit. And these are basically defined by a span of Pauli matrices or plus identity matrix. So we have set of gates, for example, Hadamard gate, you already see most of those, as I said, Pauli gates, Hadamard gates, and for case of a 2-qubit gates, we have CNOT gate, control Z gate, swap gate, etc., etc. You also, of course, talked about in the morning the rotation gates where you're implementing your trainable parameters, etc. So the thing is, let's talk about a little bit error in quantum circuits. So I got a really nice question this morning actually saying that which type of implementation of a quantum gate is more efficient. So the thing is, the efficiency can change how you're embedding this, because each of these rotation gates are actually embedded by a set of phase gate. Depending on how precise you want the rotation to be, you're basically implementing a set of layers and layers of rotation gates. Same with CNOT gates. For example, if you want to correlate multiple qubits together, you embed basically layers on layers of CNOT gates. Whenever we talk about error in quantum computers, generally people are talking about how many CNOT gates they implemented in their circuits, because most of the error is coming from the CNOT gates. The problem is, it also depends on the phase gates, because depending on the precision that you require in your rotations, you might end up embedding too many phase gate to implement that particular rotation. And then you're basically increasing the depth of your circuit. which means that it's not going to be coherent anymore after that many applications. Okay, so if you want to think about how can I apply my particular algorithm in a quantum circuit in the future in a quantum computer, you have to think about both CNOT series that you are applying, as well as the phase gate that you are applying, not phase gate, but the precision of your rotation gates together. So rotation gates, as we were just talking about a second ago from a question, rotation gates are basically implemented as literally rotations on your spin states, for example, qubit states. Your qubit state, if you're starting from 0, as we talked about earlier, 1, 0, and 1 is basically becomes 0, 1. So what we are doing with rotation gates are basically implementing a rotation, and with respect to the precision that the theta that or phi that you're implementing in your circuit, the amount of phase gate that you have to implement changes. The thing is, you don't see this on a software because these are done in the background, but actually that's what, for example, Qiskit does. If you open up Qiskit, you will see basically set of phase gate in your circuit on a hardware. So yeah, these can, as I said, yeah, these can all be implemented by series of phase gate depending on the angle, etc. Okay, so what type of operations we have? We talked about the Pauli gates, and each of these gates operations, of course, give you a different eigenstate and different phase. For example, X gate basically flips the spin state that you have. The Hadamard gates makes a eigenvalue, mean state of 0 and 1. So depending on what kind of state that you want to prepare, you can choose a set of rotations or Hadamard gate that you need. So these are very neat, useful cheat sheet basically. So I want to give it to you to observe. And most important, the CNOT gate, as you can see, the entanglement is coming from this particular identity. So basically, your end state depends on your X, your initial state. Sorry, I shouldn't say initial state. Your first state. If it's 0, your result will be 0. There's nothing will be applied. But if it's 1, then you will get X plus Y in your final state. That's how you get the entanglement structure. Okay, so let's talk about variational quantum eigensolver. As I told you, this is basically, very basically, a classification problem. You have a Hamiltonian, you have a lattice field theory that you want to simulate, you have a Hamiltonian, you want to apply this Hamiltonian and basically diagonalize it. As we talked yesterday, the problem, if you have a very large Hamiltonian, you cannot basically diagonalize it by hand because it's gigantic. It will crash your computer. You can't even write it as a matrix form. So we introduced tensor networks as an efficient way of simulating your Hamiltonian, or you can use Monte Carlo algorithms or a variational quantum eigensolver. This has also been done using machine learning applications because the challenge of diagonalization of a Hamiltonian is so hard. People also investigate all sorts of different types of algorithms to do that. So how does this work? So when we have, as I talked about earlier already, Hamiltonian, one case the following matters, the compute ground state. So the goal is to compute either the ground state or from the ground state, step by step go up. We will compute in a minute both the ground state of a Hamiltonian, of a given Hamiltonian, and the first excited state. So first of all, why and how this works. So when you have a Hamiltonian, no matter what state you try to compute, it should be greater, the expectation value has to be above ground state, right? So by that, you basically have a minima that you can achieve, optimum minima that you can achieve in your ground state. So what you can do, you can just optimize your circuit until you hit this ground state. That's the entire idea about this. So you have a minima already, your state, your entire quantum circuit is bounded from below, so you can just minimize the circuit as you've been doing since this morning, right? It's basically simple machine learning. We can take the gradient of the circuit, as Sergey showed you in the morning. You have the parameter shift rule. You can apply parameter shift, take the gradient of your circuit, and optimize all your trainable parameters depending on your ansatz. And you can use all the ansatz that you implemented this morning today here as well, and see how it goes. The one thing that you need to be very careful about in terms of machine learning applications of data analysis, you don't actually care that much about what type of ansatz you have. Most of the time, a generic enough ansatz will get you to the state that you want to end up with. Of course, efficiency will change. For example, if you have a convolutional-like ansatz, it will make your life easier in terms of optimization if you're trying to optimize for a image type of thing. In here, the problem is you're simulating a Hamiltonian, okay? Depending on your ansatz, you will always find a ground state. You will always find a minima, and probably it will be close to the original minima that you're trying to achieve. The problem is, if you're simulating a Hamiltonian, you probably want to get a physical state, physically meaningful state. So it might not be always possible to have a random ansatz and achieve both the ground state and the physical behavior, physical symmetries in your ground state in the, of your ansatz. So you need to be really careful about how to choose your ansatz in a Hamiltonian optimization scenario. So yeah, in terms of variational quantum circuit, what we are doing is we're basically computing, as I showed you here, computing expectation value. So this unitary is basically your ansatz. Okay, you apply series of rotations, and C0 gates, whatever, you choose your ansatz accordingly, and these unitaries are basically your ansatz. Okay, this is basically just rotation of it. Sorry, not rotation, Hermitian conjugate. And the zero gate is basically zero gate. Zero state is your initial state initialization. Okay, there's no magic. You just minimize it with respect to phi until you hit the ground state. Okay. Yes, sure.
So we know that this psi should be normalized, right? But is there any reason that you explicitly write down this normalization in the first equation?
Sorry, can you?
Is there any reason that you explicitly write down this normalization condition? Because we all know that this should be normalized.
Yeah, of course. That's why I wrote it. I mean, when you calculate it in a quantum circuit, it's automatically normalized. But I mean, for example, with tensor network, if we are doing it with tensor network, you should be normalizing it because it doesn't automatically normalize it. Okay. It's just mathematical notation. I mean, yeah. Quantum circuit is already normalized. It's unitary. Yeah, so the question is, you can have an arbitrary Hamiltonian, right? So how am I gonna embed an arbitrary, let's say, random Hamiltonian? Let's say I have interactions, I have bosonic field theories, etc., etc. My quantum circuit is only fermionic, right? Because I have up and down spin. I can only have up and down 0 or 1 qubits. I cannot have a bosonic structure in terms of Hamiltonian. So how can I embed, let's say, a really complex Hamiltonian? What we do is we basically decompose the Hamiltonian to express it in terms of Pauli matrices and identity operator until we achieve this Hamiltonian structure. Otherwise, there's no other way to embed this. So we basically write the Hamiltonian as a product chain of Pauli matrices with a coefficient depending on your Hamiltonian, and then we embed this terms into our variational quantum eigensolver and then optimize it and get a ground state. Okay? Yeah, as I told you before, this is very, very similar to what Sergey showed you about a classification problem. The only difference is, as you can see, I'm getting the Hamiltonian from each and every qubit that we have. Generally, in classification problem, we basically trace out the rest and get one measurement from our circuit. But now we have to apply and get a result from each and every site that we are trying to embed, okay? So connection to the yesterday's lecture, we talked about tensor networks being a representation of a quantum circuit, right? So the beautiful thing that I got another question about comparison between fully connected neural networks and quantum circuits. So there, I don't know which one you asked it before. So the question was, is it connected? How can I embed a fully connected neural network into a quantum circuit? Yes, we have these layer structures and everything, but there's actually no mathematical comparison between a fully connected, not even just fully connected, between any neural network that you study to a quantum circuit. So there's actually no comparison whatsoever. The only reason that we are calling this quantum neural network is because we are embedding this layered structure, and then we have a reasonably comparable variational ansatz that we are optimizing. In case of tensor networks, they are exact. There's a mathematical one-to-one transformation from a matrix product state to a matrix product state like quantum circuit. You can exactly convert a tensor network into a quantum circuit, simply because quantum circuits is basically a subset of a tensor network. As I told you yesterday, you can basically, if you open up Qiskit or PennyLane or whatever quantum algorithm, the quantum package that you're using, if you open up the simulation, you will see a tensor network underneath. You're basically non-optimized tensor network, let's say. Because as I told you yesterday, we are applying all the singular value decompositions and everything, but in terms of quantum circuit package, they don't obviously apply a singular value decomposition to your tensor, because otherwise you will basically approximate it. Same goes for 3 tensor networks and multiscale entanglement renormalization ansatz. We can have a mathematical prescription to convert them from classical to the quantum. We can basically see the tensor network as a less efficient classical representation of a quantum circuit, in a very crude manner. Okay, so let's do some hands-on, shall we? Let's do variational quantum eigensolver. So I want you to please open, if I can find it, not here. Where did I put? Ah, yes. So I want you to open VQE example, please. You can already open the VQT and time evolution notebooks too, because we will basically step-by-step go through all of them. So in here, if my students are here, right? By the way, they are gonna win. They are really good. So I'm basically gonna show a simplified version of the project they are doing right now. So what we are doing is basically, I want to show you from a research paper, I got this, actually I wrote a paper on this as well. So what we are doing is we are trying to find the ground state of a nonlinear sigma model. So you see here 2 terms where the first term here, why don't I have the, yeah. First term here, you see the kinetic term. So basically, it's a diagonal term that you have in your Hamiltonian, and then we are implementing interaction term. You don't need to know what the structure is. It's basically a bosonic field theory, so it's infinite dimensional. In order to embed this kind of field theory into a quantum circuit, obviously we don't have infinite amount of Hilbert space, right? So we need to truncate this Hamiltonian. So there are a couple different ways of truncating this Hamiltonian. In the time evolution example, I'm going to show you a different way. In here, what we did is basically we choose a limited amount of angular momentum state to be able to reduce this into 4x4 matrices. So each term is basically reduced to 4x4 matrix, right? As you can see. I'm giving it to you. You don't need to do the computation by yourself, but if you're interested, you can just open up my paper and see how we truncate the Hamiltonian. Okay, so now you're seeing this matrix, you will ask me, obviously, how on earth I'm going to put a 4x4 matrix on a quantum circuit. So the thing is, as in C0 gate, C0 gate is 4x4 matrix as well. So I can represent each of these interactions as a 2-qubit interaction, a 2-qubit operator, right? So I need to convert this and write them one by one in terms of Pauli matrices. So how does it look like? So as you can see, the H0 is the interaction term. As I told you, it's diagonal. This is what it becomes when you try to write it in terms of Pauli matrices. It gets really, really long chain, becomes a really long chain. So this is basically, this particular term is one interaction between two sites. So it's basically what I'm doing is I have one site represented with 2 qubits, because if I'm taking a 2 qubit, I'm basically having, let's say, 0, 0 to this. So my 0 now is 1, 0, 0, 0. So instead of representing it 1 qubit with 2 index, I'm basically representing my new state, new site, let's say, with 2. Sorry, somebody said something. Can't hear you. No questions? Okay, perfect. So I'm basically trying to represent my 4x4 matrices in terms of 2-qubit operations, okay? That's why you see 4 terms in each term. So this thing is my interaction term. So two gates, 2 operation will go to the first site, and 2 of them will go to the second site. Yes. I can't hear you.
So whether you go to a 2-qubit basis or a Pauli basis, which one is?
You have to do both. So the question was if it's more convenient to go to Pauli basis or
2-qubit basis.
Or 2-qubit basis. Okay. So I need to go to 2-qubit basis because I'm truncating my Hamiltonian. As I told you, this is an infinite Hamiltonian. I can write it as, I don't even have enough space to represent it on a board, right? So I need to truncate it. So what I decided to do, I can represent it, I can truncate it to the 1-qubit basis as well. But then I'm losing too much information from my Hamiltonian. I can represent it as a 3-qubit basis as well. Then I have a lot of information, but then my quantum circuit will get very large. Can I simulate that on my computer? That becomes a question. I can definitely cannot put it on a quantum circuit because I think you're allowed to simulate maximum 7 qubits on IBM quantum circuit right now if you're not paying. So yes.
Yes, a stupid question. The normal Pentium or Intel processor, like a normal computer on like a normal workstation, I mean, how much you can simulate, like how far you can go in the qubit?
In Qiskit, if I'm not mistaken, there's a hard cut at 30 qubits.
I see. Thank you.
Because, well, it depends on what you're trying to do as well. For example, if you're trying to do density matrix representation on your computer, I realized that 16 qubit crashes my computer. But my computer can be different than yours. Maybe you have more expensive computer. You can simulate better one.
Okay, thanks.
So, yeah.
Thanks.
Okay, so the second question was Pauli matrices. I have to represent it with Pauli matrices. I don't have any other choice because my quantum circuit is written in Pauli basis. So I have to write it. I cannot put a random matrix on my quantum computer. So I don't have any other choice. Even if I had a bigger representation, bigger Hamiltonian, I had to convert it into Pauli matrices, but the chain would have been longer. Okay? So one term will have more Pauli operations. By the way I calculated this is very, very brute force. I'm basically scanning through all the Pauli matrices until I get the original matrix. So it's not very sophisticated. So don't worry about it. Okay? So let's try to try to simulate this, try to find the ground state. So first, I'm basically importing all the necessary libraries. I'm gonna use PennyLane as you did this morning. And I'm gonna simulate this for different beta parameters. Beta is basically my coupling term, okay? Coupling strength is beta. It's 1 divided by coupling strength, but whatever. It doesn't matter if for this case, it's just you're learning how to simulate a Hamiltonian, okay? So I'm setting from 0.7 to 1.8, just as an example. You can simulate it for more if you like. It's totally up to you, but it will take longer if you have more points. So as you can see here, this gigantic thing is my interaction term, okay? So I basically write each and every term up there. This interaction term is written in terms of PennyLane's Pauli matrices. So as you can see, let's go through the first term, for example. I have Pauli times identity times another identity, another Pauli x, right? As you can see, it's exactly this particular term, okay? And as you can also see, it's applied to N0, N1, N2, and N3. These are basically, for example, if I'm trying to simulate the first particular qubit, let's say, I have, since this is an interaction term, this is site 1. This is my site 2. I'm basically applying the first identity x here and identity x here. Okay, that's all I'm doing. So this is the key. Up there, I have the kinetic term. I obviously decompose the kinetic term as well. And you can see it's identity, identity, identity z. I think I wrote it here too. Yeah, it's just 2 qubit because kinetic term doesn't have interaction. So it's just one side, other side, next side, the other side. Okay, it's a diagonal. So what I'm going to do is I'm going to construct this Hamiltonian for a arbitrary different beta. Okay, you can investigate this Hamiltonian and try to find if I introduced any bugs or anything. Feel free to find my mistakes. So all I'm doing is, so the Hamiltonian class in PennyLane takes two separate inputs. Okay, you need to separate the coefficients with the interaction terms. So basically, when you write it as a QML Hamiltonian, this has coefficients of each term. So if you're adding a plus sign, you have to separate the coefficients into this coefficient list, and then you have the kinetic and interaction terms. Okay, that's all I'm doing. It's not really magic. Then let's compile this. So let's try to do this. I think I'm doing this for 3 sites, if I'm not mistaken. Yeah, it should be for 3 sites. So let's try to do this with exact diagonalization first and see how it behaves. Because it's 3 sites, I should be able to compute this with exact diagonalization, right? So that's what I'm going to do for first, for every single beta that I introduced up here. I'm going to scan over my energies and try to simulate this. So let's get the result. As you can see, for different beta, my energy density changes. So what I did is basically here I'm finding the eigenvalues of my Hamiltonian. QML matrix basically converts my Hamiltonian into a matrix. If you want, you can even plot this matrix. Let's try that too. Let's say, as you can see, this is the real structure of my Hamiltonian, right? As you can see, it's Hermitian. So yeah, basically this is 62 by 62, I believe. Yeah, so I'm plotting the real terms because obviously I cannot plot imaginary, both imaginary and I think imaginary I can imagine. Yeah, imaginary is empty. So I'm basically plotting the real portion, okay? And as you can see, excited state is above the ground state as expected, and there's a mass gap in between. So we will investigate this below. And as expected, as I increase my beta, my energy density drops. The y-axis is my energy density. I'm dividing it by number of lattices that I'm simulating. Okay? Now this is exact diagonalization. This I can do. It's simple because I have only 3 sites. The problem comes if I increase my number of sites. That's I'm not going to investigate, but it's going to be your homework. So you can take this home and play with it and try to increase the number of sites, try to change your ansatz and everything. Okay, let's talk about the ansatz. So I defined here 2 different structures. I'm calling them by simplified 2 block. If you're interested in how this simplified 2 block is designed, I put 2 papers over here. You can just go inside and check it. These are basically designed to prevent gradient loss so that you won't hit to a barren plateau, which is a very huge problem in quantum computing. If you increase the number of qubits, you will start to realize that your gradients will vanish. So in order to prevent that, up to some point, they offer something called simplified 2-block structure, okay? And for U3, I'm basically using U3, basically it's 3 different terms with the rotation. So it's rotating both in Pauli Z, Pauli X, and Pauli Y axes. It's complete rotation, okay? And I also wrote a simplified 4-block just for your entertainment. If you want to play, it's doing the exact same thing. And you can even define different entanglers. For the entanglement, by default, I'm using CZK operator, but you can experiment with C0 and any other thing as you want, okay? So the ansatz, the entire ansatz, the way I constructed it is basically a matrix product state. As I told you earlier, there's a one-to-one correlation, one-to-one comparison, mathematical conversion between a matrix product state and quantum circuit version of matrix product state. So what I'm basically doing is like a staircase, I'm applying operators. So let's take, for example, 4 qubits, okay? I'm creating an initial operation to initialize a 2-qubit structure. Then I'm basically implementing an interaction gate like this. And similarly, at the bottom, I will implement an interaction gate like this. And to have a periodic boundary condition, you can basically have something like this. Okay? So it's basically applied to the last 2 qubits and the first 2 qubits. Okay? Is there a question, guys? No, you guys just talking to each other. Okay. Sorry. I can't hear you.
No, we are just trying to understand the circuit, this input and then goes to the output. There was a circuit there. No, below. Yeah, this one. So you have 6 inputs and that goes through all these gates and then finally you find out your outcome. Yeah. So this is what,
as you can see, the last portion is the periodic boundary condition term. I'm applying, so 2 qubit is 1 site, right? Yeah. So I'm applying 2 qubits here to 2 operation here. Then I'm entangling it with the above 2 qubits so that it's completing a full circle, okay? And here it's the same. So basically I'm applying chunks of qubit entanglement together. So it's like a staircase, okay? You can define a completely different structure. I just wanted to show you that there is a one-to-one correlation between matrix product state and the quantum version.
Can I ask a separate question? So let's say I want to write down a fermionic Lagrangian in the while basis. And I want to write down the Dirac equation in the while basis. using
what basis?
while basis, like 2 component, not 4 component.
Okay.
Will this work?
Yeah. You just need to convert it to a poly basis.
Yeah. This is why I asked. So,
Yeah.
so can you set a problem for that one?
Sorry?
Can you set a problem of that one? Write down the
Right now?
later on. Yeah.
Sure,
So,
I can look it up.
Yeah,
have to
I
look it
can
up.
try actually because isn't
There should be some examples on Schwinger model.
I
You
see.
might want to look. So
Okay.
I remember there are so many papers on Schwinger model which is using similar structure. You can look it up. I saw a couple of GitHub notebooks that you might be interested in.
Another stupid question. So another question is if you look at the propagator of a Majorana fermion,
Okay.
than a Dirac fermion, they look different. So can you represent those fermionic propagator in terms of some gate and show them that they are different?
Yeah, you can, but you need to do the decomposition. I don't know on the top of my head how to do the decomposition. Yeah, I need to work it out.
I
as
see.
you do.
I see. Thanks.
My pleasure. There's no, I think you can use Jordan-Wigner transformation. They're generally done by Jordan-Wigner, which brings you a chain of Z coupling. So, for example, I have an example on top of my head. It's not going to be exactly the same term, but for example, let's talk about Hubbard model. In Hubbard model, I have a term like T minus T, let's say Ij. I have C dagger C plus remission conjugate. So this C dagger C is basically my operator on my spin states, right? So what I'm doing is, in order to represent these, I have to apply, because as you can see, as you said, these are basically Weyl fermions. So what I need to do is write it in terms of Jordan-Wigner transformation. And when you do the calculation by hand, it's, if I remember correctly, it will become something like poly Z I times sigma minus, and C dagger will become sigma plus. I might be doing some typo, but you can do the computation. Sigma Z. Okay, so each of them is coming with a chain of Z. So if you're doing something other than nearest neighborhood interaction, this chain will get longer, so that you have to implement all them by one. Okay, so probably you need some kind of Jordan-Wigner transformation. Or if you're using, for example, two-dimensional Hamiltonians, there are more efficient transformations than Jordan-Wigner, but they're quite complex. And I've never worked on them so far. You might want to look into it. There is one paper that I know I can show you. Yes.
That's a related question. So here, if I try to use Jordan-Wigner transformation, then there I have lots of products of the sigma z's there, right? But then, as you said, when you apply like more gates, and it will increase the errors and make the system decoherent. So, does that limit the size of the lattice that we can simulate as well?
You can work with only what you have, unfortunately.
So what is kind of the maximum size? I mean, given that we have the best errors on the currently realized quantum
Depends on your
computer.
application. I cannot give you, like, I've never seen a good physical application that studies both physics and proper quantum circuit at the same time. They have to do the simulation. And I've never seen on a quantum circuit, because with the error mitigation and everything, as far as I know, let's say, even if you have access to 100 qubits, out of 100, only 6 qubits are actually valuable. So you're very much limited.
Thank you.
My pleasure.
Yes.
But you can, of course, do the simulation.
Yeah, if you wanna correct a bit flip, single qubit bit flip error, you need to introduce 2 additional qubit
Wow.
to correct the bit flip. So
There you go. By the way, there's external error correction techniques as well. After you compute everything, you can, so that's really stupid approach, but it actually works. So what they do is, for example, you have a series of CNOT gates, etc., and you know how much error one CNOT gate will bring you, right? So what they do is basically add multiple more CNOT gates just to get worse error. And then since you have the result for what you get in the initial circuit, and then you get more and more worse computation, and what you do is basically extrapolate your result to the non-error computation. It's a really efficient, really simple, but really efficient way of doing it. And you don't need to do any quantum calculation. It's just a simple extrapolation. Okay, let's move on. Any other questions? No? You're good? Perfect. So yeah. Oh, I'm stuck. Where was I? Okay, so yeah. So what I'm gonna do is I'm gonna simulate a 6-qubit circuit, and I'm basically applying my ansatz with my weights. These weights are randomly initialized. I don't care what they are right now. And I'm simulating, just to show you everything, I'm simulating beta equals to 1. Okay. And I'm taking the expectation value of this Hamiltonian. Okay. So I just wanted to show you how the circuit looks like. And you can basically see the comparison between exact diagonalization and whatever the random circuit that I get. As you can see, initially, the difference is huge. So what we're gonna try to do is try to get this Hamiltonian result closer to this result, okay? Because it cannot be lower than that. It has a lower bound, okay? This is my entire ansatz. As you can see, it starts from the 0 state, and then I'm basically applying this ansatz and measuring calculating the Hamiltonian expectation value up, down here, okay? So in the below code, what I'm doing is exactly what you did this morning. It's basically, well, I'm writing everything more explicitly so that you can see, oh no, actually I'm using Atom Optimizer as well. Oh, that's great. So it's exactly what you did this morning, okay? After this point, it's basically optimization with an Atom Optimizer. You're taking the gradient of your circuit and then optimizing it each step. So it's machine learning problem after this point. After you embed your Hamiltonian, choose your variational circuit, you have the variational eigensolver. That's it. There's nothing different than machine learning application, okay? It's basically solving a differential equation using a quantum circuit. Same thing. Well, similar concept, let's say, okay? So what I'm doing is I'm basically writing it. Let me actually run it because it will take, oh, great. Now I have a series of errors because I didn't run the first one. Great. Okay, it's gonna give some warning because I didn't check. So what it's doing is now basically it's running a for loop for every single beta that I initialized on top over here from 0.7 to 1.8. And for each and every one of them, I'm gonna use the exact same ansatz, but you might wanna explore different ansatz as well because it is known that sometimes when you change the coupling, it's getting harder and harder to optimize your circuit. So you might need a deeper circuit, or you might not need a as deeper circuit as I implemented here. It's totally up to you. You can play with it and try to get maybe more efficient results, okay? So as well, it's already did one step. So as you can see, as you do in the Hamiltonian, what I'm doing is calculating the expectation value and dividing it with the number of sites that I applied. So this is basically the energy density. And the steps is basically epochs that you were implementing this morning, okay? So this will take a while, still running. And yeah, so energy for beta 0.6. Yeah, it's basically writing that at beta equal to 0.8, I get this particular energy. Okay. Then at the bottom, oh, it's another step is done already. Okay. So there's 12 different steps. Please do run it right now because it will take time. So then what I did is I basically compared my first exact diagonalization with variational quantum eigensolver. And as you can see, you get very, very close results. It's exactly the function fitting. Nothing more, nothing less. Machine learning is just fitting. Okay, I will wait a little bit for you to digest. Then I will show you how to do it for another eigenstate. Any questions so far?
So so I'm still getting your graph. Could you show the other graph, the comparison against the exact solution?
This one?
Yeah, so the red is the exact solution, and
Yeah.
then blue is the one that you get from VQE.
Yeah.
It's supposed to be approximation.
Yeah,
So by construction, VQE cannot be smaller than red curve then.
exactly.
Okay.
If it's smaller, that means there's something very wrong. Yeah, while we are waiting for this or your questions, I'm going to tell you something about what we experienced while writing the paper for this. So what we tried, for example, for the ansatz is first time I tried it, I designed something, let's say, let's make a simpler case. I tried something like this. So same thing over here. So what I did is basically I thought, okay, I can choose a random variational ansatz. It will give me the same result. Why would it give me anything different? So I constructed MPS with deep chunk of blocks. So the entire thing is one block of the matrix product state. This is the second block. This is the third block, etc. Okay, so I thought, why not? Why not? It will give me a different thing. So as I told you earlier, this exact construction gave me ground state perfectly. There was no problem. So what we check is we wanted to study physics, right? So what we checked is in this scenario, we check the entanglement entropy to find the charge of the physics that we are studying. And for that, you're basically computing the reduced density matrix, sorry, von Neumann entropy of the central reduced density matrix. And what we realize is it's completely gibberish. It doesn't give us the correct charge of the model that we are trying to achieve. So then what we realized is we actually cannot implement just a random variational circuit for the optimization because we are studying physics. So we changed the structure. If you know, there's something called time evolving block decimation for time evolution, as the name suggests, for the matrix product state evolution. So I took the idea from there and implemented, instead of something like this, I implemented blocks in states. So this is one layer, and then I implemented another layer, etc. What this does is basically implements some sort of time evolution type of structure to my state, and then it optimizes my charge exactly where I need it to be. Okay, so when you're studying physics, you might need to actually look into your ansatz and implement some certain symmetries in your Hamiltonian to be able to achieve the correct final state. Final state is not the correct term. Eigenstate that you want to achieve at the end of the day. Okay, so applying random ansatz will not bring you the physics that you want. It might bring you the ground state that you want, but it's not the answer every time. Okay, so So it's important in physics to know what's happening behind the machine learning. Any questions? Happy? Everything is clear? Wow. It's not clear to me. Yes. You had a question? No? Okay, so let's try to find the first eigenstate, shall we? Are you running or is it done for you? Is there anything wrong? Do you want to discuss that you're not convinced? Maybe I did a mistake in the code? No? You're free to find my mistakes, by the way.
Can I ask you one
Of
quick
course.
question? So that plot comparison was the actually the ground state energy. If you actually compare, that is actually the energy of the ground state, right?
Yes.
Yeah. So if you actually compare the ground state, is it actually very similar to the exact diagonalization?
It might not be. That's what I was saying.
Oh,
So
okay.
that
Yeah.
depends very much on your ansatz.
I see. Okay. Yeah.
So
Thank you.
if I give a very bad ansatz, it might be different. It might be a ground state. So because this solution is not unique, right? You can get same ground state with wildly different same ground energy with a wildly different ground state. Because it's just adjusting it accordingly.
So if I'm interested in actually getting the right state, other than getting the right ground state energy, is there any like a trick?
Yeah,
Or-
so what we did was embedding exactly this time evolution block decimation. But for example, there was a paper that I was reading we were talking with you guys as well, on Hubbard model, for example. In Hubbard model, I erased it already. There's a hopping term in the beginning. So in that paper, they basically show that if you apply hopping term as a time evolution step, you get much better results in terms of physics. They implement different tricks like that. So if you implement the symmetries that you know in your Hamiltonian into the variational state, like because time step in there is basically just a rotation, right? So you can implement it as a rotation gate and it will fix the symmetry for you. So there are different tricks. Any other questions? What time do we end this session? At 4? Dear me, okay. Let's do the first excited state, okay? So for the first excited state, what we need is the first ground state. So what I'm gonna do is basically, oh, this is flying around. I think I broke the mic. Okay, so what I'm gonna do is I'm gonna write the first ground state as a projection operator. So it's basically gonna be a regularization term in my loss function, okay? So what I'm gonna do is I'm gonna define a projection operator for the ground state, which is written as this. So what this gonna do is basically project my any state onto my ground state. And then if I write my loss function as an expectation of Hamiltonian plus any state times 0, my handwriting is gigantic, pi, this will basically act as a regularization term and push my ground state to the first eigenstate, right? Sorry, I should say second eigenstate. Yes, you got the point. So it's basically acting like a regularization term in your machinery that Ramon told you about this morning, no, yesterday morning. So it's basically acting like a regularization term and pushing your ground state up. That's what I'm exactly doing. So it's just basically what you did for machine learning application. So what we are gonna do is we're gonna calculate the ground state first, and then using that, I'm going to calculate the first eigenstate. So I have to go write, where do I write the states? Let me see. So this is the expectation value of my function. Oh, I think I'm saving them. Where's my current state? Am I saving them here? Okay, yeah. So for example, here I'm basically computing this exact term. So expectation value plus the projection operator as shown here. Okay. So I'm modifying my cost with respect to the current state, and the state is given where? Do you guys see it? I think I'm right here. So QML state, it returns you the state of your quantum circuit. Yes.
So, is it with the ground? I mean, let's say you have a H0 Hamiltonian and you are using the ground state to find out the expectation value of some interaction, like perturbative quantum mechanics, or is it different here?
I don't understand. Say it again, please.
So you have the ground state wave function of H0 Hamiltonian, and with that you were trying to calculate the expectation value of some H interaction.
No, interaction term is in the Hamiltonian already.
Yeah, so this is not exactly the way we do perturbative quantum mechanics. It's little different.
No, there's no perturbation at all.
Yeah. So
this is the beauty of Hamiltonian.
Yeah, so
mechanics.
this is where I got amazed actually.
I absolutely hate perturbation theories. This is exact calculation.
Yeah, so this is why I want to convince myself that it is because I don't see interaction term there.
Yeah, exactly.
Yeah, so
everything is in the Hamiltonian. Okay.
It's kind of hard to digest now, but yeah.
So let me show you. So as I showed you in the beginning, very beginning, this is your interaction term.
Yes. Yeah.
That's it. There's no perturbation.
I got it. Yeah.
This is just
but then this has a caveat, like unless you can decompose into sigma matrix or Pauli matrices, you cannot do it, right?
Yes, you can.
Oh.
Everything has a balance.
This was a question I was planning to ask. Like, I know I can do it with fermions, I can do it with complex scalar, but there are systems that I probably like if I have I can still do it. Like if I have a SU3 fundamental, I can still try to break it and try to do it, but probably there would be some I cannot break it into Pauli.
Even here in this example, I'm losing a lot of information. So I'm truncated the infinite Hilbert space into 4-dimensional Hilbert space. I already lost a lot of information.
I see.
So it's even in this stage, even when I can do it, it's extremely limited. So for example, we are comparing in the paper with the tensor network methods. Obviously, this is classical method, right? It's using exactly the same structure. I still need to truncate it, but I can truncate less because it's a classical computer. I have more RAM. We have a server at the university. We can just dump it there and calculate it for like a couple days and we get the result. And we see that the difference is huge. So quantum circuits are very limited, but we need to explore.
Thanks a lot. Yeah, thanks. It's clear. Okay, so I guess if I'm not finishing it here, I won't be able to show you the rest. So I will leave you to explore the second one. And at the end, I'm basically computing the mass gap between the ground state and the first excited state, which is basically the difference between the energies, expectation values. Okay, that's it. So I guess we can have a break. Yeah.
Yeah, why don't we have a break, and then if you have questions, maybe you can talk to Jack during the break, and or maybe if you come back, then you can try to take a look at the example file. Yeah, thank you.
I forget to turn on the microphone. Okay, so I'm on the I want to talk a little bit about learning thermal states. So which is actually exactly the same thing as generative modeling, as Ramon talked about. And I think Sergey also talked about this morning. So what we're going to do is the problem, let me phrase the problem for you. So we have a Hamiltonian, and we want to simulate the eigenstate of this Hamiltonian at a fixed temperature. Okay, so this eigenstate is not going to be a pure state, obviously. As you increase the temperature, it's going to become a mixed state. So what you need to do is you need to represent this mixed state as a matrix, right? So what we're going to do is basically learn this density matrix of the Hamiltonian at a fixed temperature. Okay, that's the entire idea. There are lots of papers published on this, but I just chose one of them, which is really cool idea, the quantum algorithm that I talked about with you. So yeah, so let's dive in. So by the way, the examples are gonna go harder and harder as we move along. If you don't understand, just ask me. Even I don't understand everything, so we will figure it out together. Right, so mixed state. Let's talk about mixed state. So the quantum computer, quantum circuit is a pure state simulator, right? So we need to figure out a way to represent a mixed state. So mixed state is given as this row Gibbs. Basically, we are creating a Gibbs state from a set of pure states. So how can we write this set of pure states for... Okay, for example, let's say I have a phi. It can be a combination of different states, phi I. And then basically a mixed state is combination of these phi's together. So I can write rho equal to phi, for instance, okay? So the combination, so what I'm doing is basically I'm collecting the probability distributions of different states together inside the one mixed state, okay? Yeah, I already wrote it there. So as you can see, the probability distribution is just like a Gaussian that I have. So it's like a Boltzmann equation. If you study the quantum statistics in probably last year of your undergrad, it's exactly this. So this Z is just the normalization term. It's the partition function, basically, okay? It's very simple. It's exactly the statistical mechanics that you saw in the last year. So if you read any statistical mechanics book, it will tell you to use Gibbs-Delbrück-Moliev variational principle, which is basically tell you optimize free energy of your system. Okay, how we calculate the free energy, expectation value minus temperature times the entropy of the state, right? So there's a really nice paper about this. It's basically proposing an interesting algorithm where we have two different circuit structure, okay? So the first cube circuit, this is a circuit, and we are measuring the first circuit, and then taking this state that we measured, the wave function collapses here, then we put this wave function in the second circuit, and then calculate the energy. So the job of the first circuit is to calculate the entropy, okay? So it's basically, we will calculate entropy from here, take the entropy calculation because to plug it in the free energy, and the job of the second circuit is to calculate the energy expectation value of this particular state, and then I will plug it into the free energy, and then use exactly the same optimization techniques that I showed you earlier. We will optimize the theta for the second circuit and the phi for the first circuit, optimize everything, take the gradient, update all the phi's, and then do it again, okay? That's the entire idea. So let's move on to the example and try to make it real, shall we? So let's open, I think this is the last one. Oh yeah, so it says, it writes the same thing that I told you. So the second circuit learns the mixed state itself by optimizing the energy, and the first one is showing you the entropy. So if I instead of collapsing the state over here, if I just take the density matrix at this stage, I should be able to get the original mixed state that I'm trying to get. Okay, that's the entire goal of this problem. Any questions? Shall we dive into the examples? Oh, I always forget. Oh yeah, this is the exact same thing basically Sergey showed you in the morning about generative modeling. So what we are doing is basically, since you're trying to get the image out of, for example, if you're using quantum GANs, you're trying to represent the initial image from your circuit, right? So initial image, in my case, is basically coming from here. If I take the density matrix over here, it's the image of the, let's say, it's not image, but it's the state that I'm trying to generate, the mixed state that I'm trying to generate, okay? Yeah, let's go to the hands-on section. So please, in the notebooks, open the VQT example, and I'm already giving you the paper over here. As you can see, it's like last year's paper, so it's very recent. This is a currently research area, big research area, so it's one of my favorite papers, actually. I really like this one. It's not my paper, unfortunately. Okay, so as before, we're just gonna upload the tools that we need. So I'm using again Penny Lane because you're already familiar with it. And in this case, we are just working on the one-dimensional Heisenberg model. So it's very simple, one-dimensional chain, okay? You're already familiar probably with this structure. So in here, in the first function, I'm basically creating my Hamiltonian, all right? There's no magic, as I did before. This is just to create my perfect Hamiltonian. There's no, it's already decomposed for me. It's already an XY state, as you already know from the Heisenberg model. So it's very basic. I just put the terms inside together into the Hamiltonian, and I'm gonna simulate this, okay? So I'm just get the Hamiltonian. So let's try to get the matrix as before we did. I'm just gonna fix the coupling terms, and beta is my temperature. I choose to simulate 1.3, sorry, it's beta is my inverse temperature. I choose 1.3, but if you wanna try different things, you can feel free to do it. In the paper, they're basically telling you that when you increase the temperature, it's getting harder and harder to do the simulation. So maybe you don't want to increase it too much. I'm doing, so I'm going to come there, but I'm going to basically implement 3 different layers in my variational ansatz to simulate this. Okay, so let's try to get the image of my Heisenberg model. I crashed immediately. Okay, here we go. So as you already know, you probably studied Heisenberg model like a billion times. This is basically my image of my Heisenberg model, and I can calculate the eigenvalues of the Heisenberg model as you do. It's no magic. I'm basically using the eigenvalue decomposition of the NumPy, of the directly calculated from the matrix itself, okay? So now, as I told you before, we have 2 different circuits, right? So I'm going to construct the first circuit and to use it for calculating the entropy of my system, of the state, initial state that I'm initializing with. So the first circuit, what I'm going to do is basically implementing each of the qubits will have 1 Rx rotation. You can implement anything else. It's totally up to you. In the paper, they are suggesting this particular circuit as a minimal entropy circuit. But feel free to experiment with anything else. But please note that as you increase the depth of your circuit, the computation becomes more complex. So the goal is to achieve the same thing with smallest possible circuit. Okay, you can overkill everything. So then at the end, I'm calculating the probability of getting each qubit being 1 at the end of my circuit. I don't care about any Hamiltonian here. It's just gonna tell me after this rotation, this qubit is 1, this qubit is, the probability of having 1 for this qubit is 50% or 70%, whatever, okay? That's the only thing. So I don't care about any operation here, just measuring the circuit like I don't know, 100 times. I should probably write the shots here. So by the way, if you don't write shots over here, it will do the exact calculation. Okay, so you should write shots there to get the approximate calculation. So it's basically initialize it, embeds some kind of error inside your circuit, and then calculates the expectation value, or in this case, probability distribution. In this case, since I didn't write any shots, it will do an exact calculation, meaning that it's just compute the matrices together, multiply matrices together, that's it. Okay, so I'm calculating the probability distribution here. So to show you what's going on, I basically draw the circuit as I showed you. It's just Rx gates randomly initialized. That's the minimal entropy circuit. And then what I did is I'm basically initializing with a different circuit, different. So this product function is basically setting, I think I have 4 qubits, right? How did I initialize it? Yeah. So it will initialize the perturbation, not perturbation, variation of different initialization. So scan all of the possible possibilities for 4 qubit structure, and it will show you the result. So I'm gonna calculate the probability of each qubit for every possible qubit initialization, okay? And then the result that I get is over here like this. You will probably get something different because there is random initialization here. I'm initializing the trainable parameters which are embedded in here are X. Since I'm rotating each of my qubit differently, if you initialize it differently than me, it will give you that slightly different result, okay? This is the first circuit. That's it. There's no Hamiltonian. It's just calculating the probability distribution of my qubits from here. So the question is, how I'm supposed to calculate the entropy from this thing, right? So entropy comes from the definition of Shannon entropy. I think Sergey showed you 2 days ago. So the Shannon entropy is given as I log pi. I think I'm missing a minus sign. There should be a minus sign. Yeah. So this is the Shannon entropy. Basically, I'm going to collect all the probabilities, sum them up together. That's my entropy. That's it. The P is probability. So let's build a second circuit, and I'm gonna leave the execution to you. We can just discuss the result and you can play with it, okay? So I'm using again, the simplified 2 design. You can choose to use anything you want. There's no particular reason that I chose this particular ansatz. Feel free to choose anything. So this shape function basically tells me for this many layers and this many qubits, what is the shape of my ansatz. So it just makes your life easier. And I'm initializing the second circuit. And I'm basically preparing the initial state. So this function, this particular function, what it does is basically, so the first circuit gives me a set of states, right? So from first circuit, what I will get is, so it's VQC1, it will give me 1, 0, 1, 0, 0, let's say, okay? Whatever, how many qubits are there. So what it's gonna do, this particular function is basically, since this is 1 and my initialization is 0, this is basically gonna apply X gate over here. This is gonna apply nothing because this one is 0, this one becomes X, this one is nothing, this one is nothing, okay? So depending on which one is 1, which one is 0, because it's coming from the collapse of the wave function from the first circuit, I'm just gonna initialize my second circuit according to the first circuit, okay? And then from here, I already, since I'm calculating the probabilities from here, I can keep the probability of that particular circuit in mind. And at the end, I'm going to do the calculation accordingly. Okay. So I could have actually done this by hand as well, but using the function that is already prepared is more convenient. So if you want to see it as explicitly, you can just write a for loop and apply xgate by yourself. It's gonna be exactly the same thing, okay? Then after that, I'm applying the simplified 2 design because I have to apply the ansatz here. This I should write UFI, so that it basically learns, optimizes this variational circuit so that it can basically approximate my density matrix here, okay? So my density matrix is coming after. So after the training inside the circuit, I'm basically forming a density matrix that hopefully gives the density matrix of my Hamiltonian at a fixed temperature that I defined in the above definition. Okay. So for the circuit, what I'm doing is I'm embedding this VQC2 as a function and just calculating the expectation value of the Hamiltonian. Okay. And I can give any Hamiltonian I want so that you can play with it, change some variables, and see how it changes with different couplings, different temperature, etc. Initial state is basically coming from the first circuit, depending on the probability. Initial parameters is my trainable parameters. I'm going to give it from here. And weights are trainable parameters as well. For some reason, I defined them separately, but you can define it together as well. These are both trainable parameters of my circuit. And that's it. Oh, yeah. So for the second one in here, I'm basically trying to get the state of my circuit because I want to just test and see if I'm getting the density matrix that I'm looking for. Okay, so this second circuit state is where I'm going to test my algorithm. So for the cost function, this time I'm not going to calculate directly the expectation value because I need 2 terms, right? I need to calculate the free energy. So I need the entropy term plus I need the energy term. So what I'm going to do is basically, let's erase this part. So the first circuit, sorry, you're turning on and off all the time. So VQC, let's say QC1, it's giving me something. I'm measuring it here. This is giving me the probability distribution of each and every option in my configuration. And then I'm putting them into the second circuit, QC, oh, this is G, not C, QC2. And then from here, I'm going to calculate the expectation value of the Hamiltonian. All right. So what is going to happen is, since I know all the possibilities that I can get from the circuit and I'm calculating the probabilities from here, I can basically calculate the Hamiltonian for each and every possibility and then multiply the entire thing with the probability of that particular circuit. Because this is a constant, I can take it out of the trace, right? So this is basically my initial circuit, initial state. I'm taking out the probability. It doesn't need to be inside the trace. And I'm calculating this U1 is my second variational circuit. SI defines the first variational circuit, okay? The probability is coming from the first variational circuit, and SI is my all different possible state results. And as you can see over here, I'm basically, if the probability is not 0, I'm calculating the entropy with the function that I defined below, the Shannon entropy. Probability times the log of the probability with the minus sign in the beginning. And the energy is basically, as I'm showing you here, probability of that particular state times circuit. And the reason why I'm not calculating when it's 0, because it's 0, it's going to be 0. So why would I waste my time calculating that circuit, right? And then I'm calculating here the free energy, which I showed you earlier. Free energy is entropy times temperature plus energy. That's it. Very simple. And this entire code is basically doing exactly the same thing as we did for the variational quantum circuit, where in that case, we were just optimizing the expectation value, but in this case, we are optimizing the free energy. Same thing, there's a ground state, ground state is a wrong word. There is a minimum of the free energy, and we are just minimizing this, both circuits at the same time to achieve this minimum free energy that we can possibly achieve, okay? Oh yeah, so I should mention that I'm not using Atom over here. I'm just taking the gradient of the cost function and doing all the optimization by hand. But you can use the Atom algorithm as well if you want. It's more convenient. I don't know, sometimes I like to do things by hand. So it's totally up to you. I just want you to see how stochastic gradient descent looks as if it's too complicated. Okay. So I think we don't have much time. So maybe I should move forward. So let's go to the solution. So as you can see, it's just optimization as before. It's nothing different. It's a machine learning is a fitting, nothing more, nothing less, as I told you before. So we are fitting a function. That's it. As you before, I trained it for 100 epochs and I converged to a free energy. Feel free to play with eta. Apparently, I'm decreasing the eta every 25 steps. You can do the same. I put a minimum, apparently minimum deviation in the free energy value. You can experiment with different etas. You can do different things, okay? It's exactly the same. Eta is the learning rate. Exactly the same thing as machine learning does. So for the...
running rate, right?
Sorry?
Running rate, right?
Yeah, exactly. I mean, you can do it with the fancy scheduler algorithms as well. I'm just doing it by hand. I don't even know if PennyLane has that function. Probably it has. If you guys know, please teach me. I don't want to do everything by hand. I'm lazy. So yeah, that's what I'm doing. Please do run it because it will probably take a while to run. Let me try. Oh, it's crashed immediately. Of course, you have to run everything else before. Great, it's running. Oh, it's actually fast. Okay, let's run it and I will show you. Okay, while it's running, so what I'm doing here is, so VQC1 was giving me the probabilities, right? I'm collecting the probabilities. I want to form the state, the thermal state that I have. So I'm just initializing the thermal state with zeros, 16 by 16, because I have 4 qubits, 2 to the power of n. And it's complex because it's a amplitude matrix. And by the way, normally you cannot access to the state from a quantum computer. Since we are doing a simulation, I'm cheating. I can access to the quantum state, but from a quantum computer, they always promise that you will be able to access to the quantum state, but they never deliver. So let's see when we can access to the quantum state. Ah, it's done already. So yeah, now I want to, of course, construct my density matrix, which is combination of different states, right? So I'm basically calculating the state as I showed you earlier. The circuit state basically returns me states. So for every single possibility of the state configuration, I'm initializing my state with the trained parameters and putting it into my state function, adding it on together. And then if I basically plot it, so the first part in here, I'm doing it by hand. This is the exact calculation of the thermal state. If your Hamiltonian is too large, you won't be able to do it. Obviously, I choose it so that I can, small enough so that I can show you. I'm calculating the entropy from this result, energy from this result, and the free energy so that we can compare it together. So the calculation result, the reconstructed thermal state looks like this. So let's compare it with the original one, and this is the analytic term. As you can see, it's almost the same image. Of course, there's some differences, but you need to optimize the ansatz to get a better structure. That's totally up to you. You can play with it as a homework. I was too lazy to optimize everything, so feel free to play. Sorry? Color code? Sure, let's print it. Pretty much the same. Feel free to optimize it further. And what is happening here? Yeah. So in here, I'm calculating the free energy for different beta. And you can see that free energy increases as expected for when I increase the beta. And in the paper, if I'm not mistaken, I already told you this, but they're stating that with larger beta, it's getting harder and harder to calculate the optimize it to a minimum free energy. Yeah, so you can play and see for yourself if it's harder, or maybe you can get a better result and publish a paper on that. Yeah, so that's the thermal state. So as you can see, it's exactly the same as generative modeling. There's not much difference. We are basically created an image from the thermal state, as we do for, I don't know, image reconstruction, as Ramon showed you. Sorry, not image, guns, as he showed you yesterday morning. This morning, yesterday. Yeah. Any questions? When do we end, by the way? At 5? Please don't tell me 5. 30? Yes.
I don't think you have given the project on the temperature.
I can't hear you.
No. So have you given a project on the critical temperature or this one? Critical temperature on the phase transition?
I
No.
just did what they are doing in the paper.
Okay.
It's not a project that I did. It's just I prepared the paper as an example for you. That's it.
So let's say you have the beta here, which from there I can extract the temperature. So is it possible to calculate the critical temperature in this sort of framework?
I would imagine so.
Another question is, like, if I interpret, like, let's say I want to study the transition of one vacuum to another vacuum, like transition probability, like variational method, that if I can apply here, I do not know if this technique will work or not. Like, I want to replace the time with some operator here, like the Pauli matrices.
I don't know what you want to do. I don't understand. Could you explain it better?
So I want so let's say there are two minimas, and the potential would collapse from one to another, and I want to calculate the time. And I want to use this quantum algorithm to calculate it.
I've never done that. So I don't know if this particular algorithm can give you that, but I would say, why not? But I don't know. I've never done that particular calculation before, so I cannot say it can give you the answer that you're looking for. Okay?
Okay, thanks.
My pleasure. Any other question? Should we move on to purely quantum optimization? Do we have time, by the way? Are we finishing at 5:30? Yeah, okay. Okay. So let's talk about time evolution, because time evolution is purely quantum simulation. So what we are doing is basically, imagine you start from a random state and imagine you have a Hamiltonian. If I evolve my state in time, I will eventually optimize my circuit to get the correct ground state, eigenvalue of the ground state, eigenvalue of my Hamiltonian, right? So that's the purely quantum way of doing optimization, basically. So let's talk about quantum simulation. So let's remember from our quantum 101 time evolving Schrödinger equation, if my Hamiltonian is a Hermitian Hamiltonian, I can write it as a unitary operator, right? So basically what I'm doing is, if I can write it as a unitary operator, I can write an exponential term for the time evolution of my operator, okay? And then I can, of course, apply the Taylor expansion to my Hamiltonian and apply it to my circuit. So what I'm trying to achieve is, in terms of a vector space of the quantum system, what I'm trying to do is to go from one state to the time evolved state, which is a smooth function. But I cannot achieve it numerically. So what I'm going to do is I'm going to step by step try to apply operator after operator and try to optimize my algorithm to achieve this state in the future one time. So this is basically done by trotterization of my Hamiltonian, which is, so if my Hamiltonian terms are not commuting, I have to trotterize my Hamiltonian exponential in this way. H delta, not delta. T is equal to beta. That's a very weird parenthesis. E minus I H delta T times N. This N is number of application of this particular operator, and delta T times N gives me my original T. Okay? You already saw this in your quantum 101. Okay, this is a very simple thing. It comes with a trotterization error. I'm not going to get into that. If you choose a large delta T, of course, you will get a larger trotterization error. But yeah, you have to compensate it accordingly. So yes, this is basically the one thing that you can obviously get quantum advantage if you have a quantum computer that without any error or anything, but we don't have. So, but this is the obvious reason why. Because, for example, let's talk about Monte Carlo algorithms that we already talked about. Monte Carlo algorithm obviously suffers from a sign problem, right? That's why we designed something called tensor networks, which we discussed. What is the problem with tensor networks? We can simulate very large circuits, very large quantum states, and everything is beautifully works. The problem is, as I evolve the time, as I apply trotter layers, I need to more and more bond dimension, and it will eventually explode. So I cannot simulate infinite time evolution with my tensor networks. In quantum circuits, I don't have bond dimensions. I can simulate infinitely many time steps. I can't in a real quantum computer, but in principle, in the future, maybe your children will be able to. So yeah, what we need to do is basically, we are again need to write the Hamiltonian as a Pauli span. So multiplication, Kronecker multiplication of the Pauli matrices, again, as always. And then let's talk about an example. Very simple thing. We know how to write a Z rotation, right? Z basically flips a block sphere, block sphere. So basically, if you have a 0 state here and 1 state here, Z operation rotates it from here to there, right? So it's basically gives you the eigenvalue of 1 from here to there. So the rotation is basically from up to down. So I know how this behaves, right? So I can basically write this Hamiltonian Z as exponent of Z theta divided by 2. The theta is basically corresponding to my delta T, right? So that I can write this entire operator as our Z operation. Just one gate, rotation, that's it. Very simple. It will get hard, don't worry. So what we want to do in terms of simulation, we always want to end up with RZ operators because we know how to write it. So we always will try to convert everything to this form with more terms, obviously, because we don't have just Z, we have multiple different combinations of these operators. For example, let's talk about another example. Yeah, that's, for example, very simple again, X operator. So how can I convert this X to Z? That's what I need to do. So there is an identity, if you remember from your Quantum 101 again. By the way, I never remember these identities. I always look up, so don't worry about remembering things. It's really, really unnecessary thing to remember anything. Okay, so you look up and you see that I can apply 2 Hadamard gates to my X operator and convert it to Z, right? So basically using this particular identity, you can solve it by hand to prove it. It's always good to prove it once, at least, when you're young. Then you will get bored and not gonna do it by hand ever again. So I'm basically applying Hadamard gate to the Z operation that I showed you before. This is exactly the same operation, and I get the EIX, right? So it's basically the same circuit with 2 Hadamard gates in the beginning and at the end. So what I'm going to do is basically, if, for example, I have this Hamiltonian term in my Hamiltonian, I'm going to apply multiples of this for each and every time step. Okay? It's as simple as that. That's why it gets deeper and deeper with every single delta T. That's why we cannot simulate entire infinite time evolution, unfortunately. So let's do some time evolution example. So please open the time evolution notebook in your exercises, and we got back to sigma models, the exact same Hamiltonian that we simulated earlier, but we are using a different truncation technique this time. Okay, so what I showed you earlier, interaction terms were written in a very long chain. If you remember, if we just go up there and check the interaction terms here, as you can see, it's gigantic list, right? So if I try to embed this every single term one by one, one single time iteration will be extremely long. And I want to optimize this as much as possible. So if you check this paper, it's not my paper. So unfortunately, it's a really beautiful paper, by the way. All other papers are beautiful. So if you check this paper, you will see that they find a really smart way of truncating the Hamiltonian. You don't need to know the details about it. They're basically using the group theory to map this Hamiltonian on a fuzzy sphere. I have no idea what that is, so please don't question me about that. So they are basically mapping this Hamiltonian on a fuzzy sphere, and then they end up with these interaction terms. These 3 J's are their interaction term with imagine this as a different basis for my Pauli's, okay? So they're writing their interaction basis, let's say, that's actually not an accurate term, but yeah, they're writing their terms as J1, J2, J3. So what we need to do is we just need to convert these as before to terms that I can act on my quantum circuit. So for that, I'm gonna return to my notes because I don't remember the identities as I told you before. So let's try to do it for J1. Do you have any idea how to do it? Can you find me a identity to do that? You should be Googling it. Okay, I will give you a cheat sheet. So I'm gonna give you 5 minutes to try to figure out yourselves, but I'm gonna show you the identity and you can figure out the circuit from there, but I will show you afterwards, don't worry. So the identity that I used is y equal to s h z h stagger. This is the phase operator. Hadamard phase and Z operator because I want to write it eventually as a Z operator. Okay. Please use pen and paper and try to drive me a circuit. And I'm going to give extra points for tomorrow's presentation to the group who can come up with the circuit. By the way, the circuit term that you're trying to come up with is J1, 0. This is the site that you're applying, the qubit that you're applying, and J1 again, 1. That's the interaction term. I can expand it a little bit more to help you. So it is identity times, this is Kronecker product. Y, this is applied to the first qubit. No, I should, yeah. 0, 1. And then times again, another Kronecker product. 1, Kronecker product, Y. So if you look at the exact qubit order, this is 3, 2, 1, 0. Okay, so the first site, second site, second qubit, third qubit, 0th qubit, and first qubit. So you're applying this as a term like this. Give me this gate. It took me so long to derive this. We don't have much time. Maybe I shouldn't do the rest. The J2 and J3, I can give the identities and they can work out together. Any idea? Okay, then since no one can find it and we have to move on. No team gets extra points. No? Okay. Okay, so what I'm gonna do is I'm gonna basically write the entire thing, expanded this thing. I'm replacing Y with the term that I put it there, and I'm just gonna write the circuit from there. Okay, so J1, 1, J0, 1, 0, equal to These numbers in parentheses, by the way, the qubits that I'm applying them to. It confuses me, so I write it on top, so that I can see it. Okay, so this is the exact, I'm just took it the equation from there and put it inside. Okay, so what it happens is basically 1, 2, 3, yeah, it's only 3, 1, 2, 3, yeah, perfect. So I have here S, H, here another SH, this is control X, because of the Z that I'm having here. Z. Okay, this is gonna be your homework. H, S dagger, H, S dagger. Okay, it turns out to become like this. So it's actually a gigantic term, right? So I'm gonna give you the identities for the other two and write the circuit, draw the circuit on the board, but you can feel free to work it out for yourselves, okay? So the identities, actually I used the same identity for the second one and added this, let me write the identity there. Also used the identity that I already showed you, HXH. So this for the second circuit, I basically got I got this 2, 3, 4. There's extra circuit, but it's empty. SH. Okay, this is the second one. And the third one is gonna become, I'm using these two identities again. They're all 2 qubits, as you can see. Okay. SH. So while I'm writing this, as you can see, there are similar terms in each circuit, right? So these terms will cancel each other. For example, S dagger S is identity, right? So I don't need to write it in my full circuit. That's what I implemented there. So I basically, since it's returning me identity, if I apply it to my quantum circuit, it will take time. It will actually apply every single gate that you apply. So you can make it efficient. If it's giving you identity, you can just remove it. Otherwise, you will get extra error. You don't need to do that, right? Yes, H here, H. That. These are also written in the paper, by the way. So you just need to put the identities into the equation, and it pops out the same things that you get in the paper. So I didn't do magic really. So so we need to implement the kinetic terms as well. So what you're gonna do is basically a phase gate, 2 phase gate will cancel each other. So it's just I'm gonna apply a RZ gate, with X's in the beginning at the end because I need to initialize the circuit first, apply the phase gate so that I can get the identity, and then cancel the circuit again. Okay, so let's do the simulation. Oh dear me, I don't have time. Okay, this time I'm using Qiskit so that you can see how it's used. It's not so much different from the penny lane, but be careful. Sometimes the notation changes, so some definitions of the matrices are slightly different in penny lane than the Qiskit. So you need to be careful if your results are not matching exactly between Qiskit and penny lane. It's because of the definition of the matrices. So I'm basically gonna run the entire thing, and as you can see, I defined each term separately. You can see exactly how it's applied. As I told you before, I'm applying 2 X's to initialize the circuit, and then a phase gate. The CP is basically the phase gate with controlled phase gate with delta T. So I'm rotating. It's basically same thing as the controlled RZ, as I showed you here, with a control gate, but it has a slightly different phase, so just to keep in mind. And then I'm applying 2 X's again, okay? And the initial int1, int2, and int3 are exactly the circuits that I should get this here. Exactly the circuits that I implemented here. So this is the first one, this is the second one, this is the third one. All right? In here, I have remove beginning, remove final, etc. These are, as I told you before, since the terms cancel each other, in order to show myself that I implemented correctly, I initially put everything here, but remove final and remove beginning basically cancels out the terms that gives me identity. So you can, if you set it to false, it will show you the entire circuit, but it's gonna be expensive to calculate. If you set it to true, it will basically remove the terms by hand. It's not removing in the circuit, so that it's gonna be more efficient. So please don't implement the gates if it's gonna give you identity. It's just a waste of resources for you. Okay, so it's exactly the same operator over here. If you want, I also implemented a plotting option. It will plot at every single step. So if you want to see the circuit structure, you can plot it there. Okay, so I implement this with delta t equal to 0.1. If you make this smaller, you will get much more accurate circuit in terms of trautherization error, obviously. But it will take longer time because delta t times n equal to your time that you want to get. So you're going to get a shorter time. Okay, so PBC is periodic boundary conditions. If you want to apply, you can. It's automatically set it to true. You basically what this is doing. It's basically an MPS, matrix product state. So I'm basically creating a matrix product state like this. Okay, that's the periodic boundary condition. If you don't want periodic boundary condition, you can just remove this. That's all it does. Okay, so then I want to see how the state evolve by taking I choose a certain state configuration, 4 different state configuration. If you want to choose a different one, you can choose a different one, feel free. And I'm gonna take the probabilities, compute the probabilities and state error because I'm using shots, okay? So it's not gonna be the exact calculation. I'm gonna initialize it different times because that's how quantum computer works, right? You apply different shots and for each shots you get a result, 1 or 0, and then you take the expectation value, which means the mean of your result. So Quantum simulator is a simulator that you can use. You can also put this onto a quantum computer, by the way, if you want. But you will get gibberish because it will have so much error because of the depth of the circuit. Okay. I'm using something called AER simulator to do the simulation. You can try different simulators. Qiskit has various different simulators if you want to use. So for the plotting, I chose a specific time steps so that you won't explode your screen if you want to plot it. But for the non-plot case, I'm choosing time steps of 41 between 0 and 4, okay? So what I'm doing is I'm changing my circuit structure at every single step. As I told you, how trotterization works, basically, I have a Hamiltonian term. For the first time step, I'm applying n times of Hamiltonian Hamiltonian term. So for each and every time step, I'm gonna apply a set of operators, so my circuit gets deeper and deeper at every single time step. And then for each and every time step, I'm just measuring my expectation value, calculating my expectation value. As you can see here, I'm applying for every single time step. And basically at the end, I'm taking the counts, because since I'm doing shots, for every shots, for example, let's say I'm only measuring the first qubit. For every shots, it will give me either 1 or 0. So I'm just gonna take the mean value, okay? For the probability, that's the probability. So I'm basically taking the counts for the state that I'm looking for. In the props key, I have different states. So it's basically taking the number of occurrence of that particular state in your list. And I'm basically dividing it by shots. Okay, that's the expectation value. Probability of getting this particular state. Okay, and if it's not occurring in my configuration, it's getting it 0. And then I'm calculating the statistical error of this occurrence, because I have limited number of shots, so that I'm not going to get the perfect results. So there's going to be a statistical error. If you increase the number of shots, of course, this statistical error should shrink down. Okay, let's run this. It will take probably a while to run. Did I execute this? Oh, wow, it's faster. Yeah, so there's no gradient, no nothing. I'm just basically increasing the depth of my circuit every time and calculating a new state at a new time, okay? Then I'm basically gonna plot this errors and state. So what I get is this. As you can see, each result comes with an error, statistical error, and my state basically evolves in a periodic condition. So these are the states that I choose as above. You can choose to simulate different states. I'm basically trying to show you the exact same results that paper shows. So you can please feel free to get for different results, okay? Any questions? We don't have much time yet. That should be fast. No questions? Should I show you how to combine them and apply it to a data analysis example? So how can we use time evolution for data analysis? Yeah? All right. All right. Let's put everything together. So I'm going to talk about Hamiltonian learning for anomaly detection. Okay? So the problem is the same as I showed you yesterday. I'm going to look into differentiate top quarks, top jets from QCD jets. Okay? Exact same problem, exact same image. By the way, this is the mean of 10,000 different images. It's same thing as Sergey showed you before. If you take the single event, it doesn't mean anything. The mean value shows you that three-pronged structure exactly coming from the top quark decay structure, okay? Same problem, I'm just implementing into a different circumstances. So what I want to do is basically I want to simulate the probability distribution of my image. Each pixel has a probability distribution, right? And this probability distribution will tell me which pixel is more probable to be 1 or 0. That's what I want to simulate. So the problem is the quantum circuit is a pure state simulator. I cannot combine since I'm trying to get the probability distribution, I need to get the density matrix of my data, okay? But I cannot simulate this on a quantum circuit because it's just simulating a pure state. So what I'm gonna do is I'm basically gonna imagine that I have the information for single image of the probability distribution of every single pixel to be 1 or 0. So what I can do is I can just sample from my image and create a gigantic sample of ones and zeros. If, for a simple example, if I basically get the expectation value of Z operator is basically telling me the probability of this being 1 or 0 of this entire circuit without anything in it. It should give me a sigmoid of data because I'm trying to get the probability by applying a sigmoid function to my data, okay? So if I sample enough from this data, I should be able to regenerate the sigmoid of my data, okay? So what I want to do is I want to create n copies of my circuit, put my entire thing into my circuit. So the copies of the circuit basically should be able to generate the density matrix of my data. And I'm basically trying to apply a variational circuit and try to get the density, reduce the density matrix of my entire data at the end of this circuit. The problem is, how can I do this? For this, I need a proper Hamiltonian so that it can optimize my circuit, right? So for the to choose a proper Hamiltonian, of course, I can use a sigma z or like you chose in the morning for the classification or quantum GAN type of example. I can use a random zx or whatever Pauli matrix to find the expectation value. The problem is, I don't know if this kind of approach will give me the entire correlation structure of my data. So I cannot use that because the Hamiltonian that I'm gonna get should capture the entropic probability distribution of my data, initial data. And Pauli Z, just Pauli Z may or may not, depending on your data, give this correlation structure of my data, right? So what else can I use? I can use a known Hamiltonian, can use a Ising model Hamiltonian, or I don't know, the more complex Hubbard Hamiltonian, for example. The problem is these kind of terms has really limited amount of correlation structure embedded these. So I don't know a priori if my Hamiltonian, my data is just locally correlated or if there are long range interactions in it or not. Okay, so what I can do, I can have a very free Hamiltonian matrix and I can basically optimize the entire thing to give me to learn a Hamiltonian that captures the entropic probability distribution. So what I want to get is basically a Hamiltonian estimator, a classical Hamiltonian estimator, because this operation is very expensive. And by choosing a random Hamiltonian estimator, I'm basically getting, creating a thermal state of my Hamiltonian with respect to a temperature. Beta is 1 over temperature with respect to a temperature. And hopefully, if I optimize this circuit enough, this should be able to represent the density matrix of my initial data. So as I showed you earlier, the Gibbs-Delbrück-Mollier variational principle states that you should be able to optimize the free energy and get the results, right? The problem is, before I knew what kind of entropy I had in the previous example. This time, I don't know, I don't even know the structure of my data. I don't know how it looks like. So I cannot construct the entropy of my data. So I need to do a trick here. So what I did basically is, since I know that free energy is log of partition function, which is coming from the Hamiltonian estimator. By the way, for the Hamiltonian estimator, I'm using a simple RBM. The Boltzmann machine. Very simple, classical neural network, single layer Boltzmann machine. To estimate. Why Boltzmann machine? Because it's an energy-based neural network, and I can easily calculate the partition function. You can use any type of neural network, but it might be too complicated to calculate this partition function for the choice of your neural network. Okay, that's why I chose RBM for this particular case. So what I'm going to do is I'm going to use that equation to rewrite my f in terms of this. So instead of E minus temperature S equal to K beta log partition function, since I don't know S, I'm going to throw it out, and I'm going to get E divided by, let's say, call it beta, divided minus K beta log, sorry, this is negative, yes, equal to S. I might be missing something. Yeah, you can fix it later. So what I'm trying to do is basically, instead of optimizing for F, I'm going to optimize for S so that it's going to be bounded from below by the entropy of my data. I know that there is an entropy of the data, and I know that it's fixed. So I can optimize to find that entropy. So it's bounded from below by the entropy value. So I'm not going to just go deep and deep and there's no minima. There's actually a minimum. But just take a look at this equation for a second. You remember that Ramon showed you negative log likelihood, right? So if you stare this equation long enough, you will realize that for a Hamiltonian that is Hermitian, this is actually negative log likelihood for a multivariate Gaussian. Nothing different, because there's Z here. So the partition so in the multivariate Gaussian, what do you have? N, let's say theta mu equal to E minus, not I, sorry, X divided by 2 pi determinant of covariance matrix, right? This is basically taken from Wikipedia. If you just search for multivariate Gaussian, you will get this. And if you take the negative log likelihood of this probability distribution, you will exactly get this function. So what I'm doing is basically, I'm assuming that my entire structure is something like multivariate Gaussian. And my Hamiltonian is basically my covariance matrix. And if I basically try to find the Fisher information, second derivative of the negative log likelihood, it's the Hamiltonian. It's my covariance matrix. So Hamiltonian is acting as a covariance matrix in this particular scenario. And if so, partition function. How am I calculating partition function? Is the eigen in this scenario eigenvalues, sum of the eigenvalues of, so the Z is equal to E minus I epsilon. I might be writing it wrong, but something like that. So the partition function is basically sum of the eigenvalues, right? If my Hamiltonian is Hermitian, it's equal to determinant. I'm missing a dimension here. Yeah, if it's Hermitian, it's basically equal to the determinant of my covariance matrix. So it's exactly what I'm optimizing it as basically exactly the multivariate Gaussian. So I'm assuming that my statistical model has a probability distribution as if it's a multivariate Gaussian. Okay? What? Yeah, so what I did next is basically, okay, what does Hamiltonian mean? I'm not going to show you the generative modeling part. You can just read the paper. I want to talk about what does Hamiltonian mean. If I evolve my state, evolve my signal and background separately with respect to this learned Hamiltonian, do I get a different signal? That's what I exactly did. So in the blue lines, I'm basically applying this Hamiltonian with respect to a characterization and get a fluctuative, a wave kind of structure from the signal, and the blue one is the background. By the way, this network is not being trained for signal. It's only seeing data, and I'm externally looking for how it behaves for the signal. And as you can see, it gives me some weird result. So the problem is, I can see that this is different from signal and background is different from each other. How can I extract the information that I can classify these? So I asked my engineer friends, and they told me, well, it's obvious, just apply fast Fourier transformation. And then if you look at the fast Fourier transformation, in the large frequencies, my I shouldn't call it signal probably, my two different fluctuations are completely changed between each other. I also calculated the expectation value at time equal to 0 state at this point. And what we get is basically, I can use this information, I can use the Hamiltonian that I learned to classify signal from background. So I did it for 6 qubits and 8 qubits. As you can see, they are giving me quite nice results for different scenarios. So you can use actually the learned Hamiltonian even to classify your object, to do anomaly detection. This basically tells me that I can learn a certain structure in my data and embed it, represent it as a Hamiltonian. This Hamiltonian, what else information does get? As I told you before, this Hamiltonian is designed to learn the entropic probability distribution, right? So for the 6 qubit scenario, what I did is basically do the direct diagonalization and see if I'm actually getting any entropy distribution from this Hamiltonian. And what I found is basically whenever I have a peak in my background probability pixel density, I get low entropy from my Hamiltonian. So it actually learns the probability distribution of my data. So the green ones are the entanglement entropy for local densities. And this solid blocks are probability distribution of each pixel for my qubit structure. And that's it. As you can see, theory is not so much different than machine learning. So you can use all the knowledge that you can learn from Quantum 101 class and apply it to data analysis. And you don't need to convert machine learning structure, machine learning things to just use it in the quantum sense. You can actually write quantum type of algorithms to do anomaly detection. Thank you. I think we are already late, so I should let you go.